Students, welcome again to Dallas Online. I'm Cyprian Mgina, and today we are going to study physics to the subtopic of projectile motion. This subtopic is under the mechanics in physics, and today we are just going to look some areas which are really very challenging whenever you are going to study this subtopic of projectile motion. First of all, we should have to know actually the applications where this projectile motion is applicable. Projectile motion, I understand that you have learned a lot about all of the basic equations with regard to the projectile motion. And after looking those basic formulas, of which I understand you have already learned, we will eventually be able to look basic applications where the projectile motion can really take up to where we can be able to see it. So there are 4 basic formulas of which I believe you know on how just to derive and to reach to that particular 4 basic formulas. So this is what we call the projectile motion. Okay, there are 4 basic formulas of which I really understand that you are supposed to have understood on how just to derive them. And later, these 4 formulas will eventually be able to take us into various applications of which we shall just be able to see very briefly. The first one you are supposed to understand is you should have to know the formula which will help you to get time of flight of a projectile motion. And after that, you should have to know the time which will really take you to reach to the maximum height. And the third formula, you have to know about the range and also the maximum height. So the projectile motion really is something like this. The projectile motion is something like this, that we are having horizontal displacement x and y direction. And the body can just be projected with a certain initial velocity of projection v0, and the body will just take this particular course until it lands to that particular ground, whenever it had been projected to a certain angle of projection, theta. And from there, we should have to know, as I've already said, about the 4 basic formulas. The first one is the time of flight. The time of flight t, the time at which the body takes from the point of projection until when it reaches to the ground. And this is just equal to 2v0 sine theta over g. This is the time of flight. The second formula is the time which takes a projectile to reach to the maximum height. The maximum height, it is this point. And this is the maximum height. So the time which takes from the point of projection to the maximum height, then this is just a half of the time of the flight, and which is just equal to a v0 sine theta over g. This is the second formula. The third formula is the range. The range is the horizontal distance covered by a projectile from the point of projection until when it reaches to the ground. So this is the range we are talking about. And this range R is just equal to v0 squared sine 2 theta over g. This is the range. And the fourth expression, or the fourth formula, which is really very basic, is the maximum height. This particular maximum height from this point to the maximum point of the trajectory. So that is the maximum height. This maximum height is just equal to v0 squared sine squared theta over g. So these are the 4 basic formula of which I understood you have already learned, and you could just be able to know on how just to derive them. So having known this, then you should have to know that actually projectile motion have got so many applications for most of the sports like football, volleyball, basketball, netball, table tennis. Really, the balls which are just being used really, whenever they are being kicked, they can just be able to move and be able to describe a projectile motion. That in a particular projectile motion, the motion of a projectile, it is controlled by the gravitational force only. And that's why sports games like football or whatever, whenever you kick a ball, the only force which controls the motion of a ball is the gravitational force. So the same is applicable to a basketball, to a tennis, volleyball, whatever, such kind of ball. Or even whenever you are throwing a stone, or whenever you are using a catapult, throwing a stone, whenever you are using an arrow, a bow and an arrow, whenever an arrow had just been thrown, it will just be able to move in such a way that as you can be able to see to the diagram here, it will be able to move from the point of projection, moving such a particular trajectory until it lands to a ground. And all of these are the applications of the projectile motion, as well as in army. For example, if the planes are carrying some bombs, they just want to hit a certain target, then a pilot, depending upon the altitude at which he is just flying, then the pilot can be able to know the speed of a plane, and then by knowing the target where he wants to hit, then the bomb can just be released to a particular position, and that particular bomb can go all the way to the target. So there are so many applications of the projectile motion. So as long as I know that you understand all of this, but there are some challenges of which we are really going to look for today. I've just tried to check up to select some few challenges which we shall be able to discuss as we are going on. So our first case is the projection of a body from a point above a ground. So we are having a simple sketch like this. That we are taking the projection point is that particular point there, having our x and y direction, horizontal and vertical directions as x and y over there, and we are having a body to be projected at that particular point with the velocity v naught at a certain angle theta. With the velocity v naught at an angle theta. And that particular projection, the body will just be able to move, take such kind of a trajectory and be able to move and be able to hit to a ground at that particular position. So we will just be able to determine the time of flight, the time it takes from the point of projection until when it hits to a ground. We can as well be able to determine even the height. If it were a building, if it was a projection from the top of the building, then we can as well be able to determine the height h. So with this particular question, you might be asked several things. Depending upon the values which will be given to you, you can be asked to determine, for example, the angle of projection, or to determine the time of flight, or to determine the height at which that particular body had been projected from that particular point above the ground. So with that particular question, we are just going to use, normally in solving any particular projectile motion, we are using horizontal and vertical component velocity. And for this case, for example, if we needed to determine the time of flight, then we normally have to use the normal equations, which starts with s is equal to ut plus a half at squared, And for this case, we'll be taking y, which is equal to, if we're using the vertical component velocity, then we are resolving this v naught to the vertical, which is v naught sine theta times t minus a half times gt squared. Remember, the acceleration due to gravity is always acting to the negative y direction, and that's why we are giving it with a negative sign there. And therefore, if we need to determine the time of flight, then as long as it's being projected from the height h, then our general equation will just be equal to y is equal to h plus v naught sine theta times t minus a half times gt squared. Now for that particular case, we are taking our y here to be equal to 0. So here will be equal to h plus v naught sine theta times t minus a half times gt squared. And if we are going to take the whole expressions into one direction, then we will be having a half gt squared minus v naught sine theta times t, and minus that much minus h, so the whole of this is equal to 0. If you look at this particular equation, this is a quadratic equation, whereby the value for t here, the value for t can just be solved. As long as a half g and v naught sine theta and h are known, you could just be able to solve for the values of t. Okay, you can be able to get some two values of t, whereby one of it could be having a negative sign and the other to be a positive, but you pick up the one which is positive, and that will just be the time of flight from this particular point to that particular point. And the second case, you can be able to look for a range. You can be able to determine for a range r. The range r, it is this distance from the foot of the building to the point where that particular body hits the ground. So to obtain for the range r, you really need to know the time of flight. You really need to know about the time of flight. So the range r, using which is equal to ut plus a half at squared, but we normally now have to use the horizontal component velocity. For the horizontal component velocity, then our x here, which is equal to the range, will just be equal to a v naught cos theta. Now the acceleration, the g to the x direction, is just equal to 0. So it doesn't exist, that particular expression. So we shall just be having this much times t. So this will be giving us the range. So for that particular case, we are just going to have to determine the range r. As long as you know the time of flight t, then you just have to multiply the horizontal component velocity, which is v naught cos theta, times the time of flight, of which you could have already obtained in the first expression. So this is the first part of a projection of a body at a point above a ground. Now let us go to our first example, and this says that a boy is standing at the top of the tall building, kicks a ball with a velocity of 30 meters per second, which lands at the ground after 10 seconds, at a distance of 130 meters from the foot of the building. A. Find the angle of inclination to the horizontal at which the ball was kicked. B. Determine the height of the building. And C. Calculate the landing velocity of a ball and the angle it makes to the horizontal at this instant. So this is a pure question with regard to what I have already said it to you. So we are going to use the same diagram, that the boy is standing at the top of the building. He kicks a ball with a velocity of 30 meters per second. So my velocity v naught there, is 30 meters per second. V naught there is 30 meters per second. And it lands to the ground. So that is the time of flight. From this point until when it lands to the ground, it uses 10 seconds. That is the time of flight. So the time there, it is 10 seconds. Okay? And it lands at a distance of 130 meters from the foot of the building. That is the range. That is the distance from this point to that point is 180 130 meters. That's the range. So the range there is 130 meters. These are the values which are given. So we needed to find the angle of inclination to the horizontal at which the ball was kicked. We are looking at this particular angle theta. So for part A, to determine the angle of inclination, actually we needed to determine the range, or the x, which is just equal to the range, which could just be solved by taking the horizontal component velocity times the time of flight. So we are taking the v naught, horizontal component velocity is v naught cos theta times the time of flight, t. And now we all know that all of the values are given. That this range is 130 meters, and the initial velocity of projection, that is 30 meters per second, and the time of flight t is 10 seconds as given. So we can eventually be able to calculate the angle theta. So we are going to have the range, which is 130, v naught is 30 cos theta times time, which is equal to 10 seconds. Then you can just be able to know that here we could just be able to have the cosine theta. This is just equal to 130 over 300. Which will just be equal to 13 over 30. So looking for the angle theta, here we are looking for the cosine inverse of 13 over 30. Cos inverse over 13 over 30. So you just take 13 over 30, which is equal to 0.433. 0.4333. So you look for the cosine inverse of that, of which you can just be able to calculate. Now looking for the cosine inverse of that much, you could be able to find that this angle theta is equal to 64.3. So the angle of inclination to the horizontal at which the ball was kicked is 64.3 using your calculator. Let's go to part B. Determine the height of the building. The height of the building is this height h. So we needed to determine that particular height of the building. So to part B, to determine the height of the building, we are using our normal equation, which begins from S is equal to ut plus a half at squared. So looking for y, then this will just be equal to h plus v naught sin theta times t minus a half gt squared. So this is our basic equation which we are just going to use. And on that case, we are putting y is equal to 0, so that we could be able to determine what is the h, which will just be equal to v naught sin theta times t minus a half gt squared. And solving this, if we proceed from that particular expression, then we can be able to get minus h to be equal to v naught sin theta times t, v naught sin theta times t minus a half gt squared, minus a half gt squared, of where we could just be able to substitute for the values to obtain h, as long as we know the angle theta. So minus h there will be equal to v naught. V naught is equal to 30 meters per second. Sin theta, this is equal to the sine of that angle 64.3. The sine of 64.3, and the time of flight, that is 10 seconds. So you substitute there 10, so minus a half gt squared. The g is 9.8 over 2, and the time there is 10 squared. So we can be able to compute for that and be able to determine what is h. So we are getting minus h there is just equal to 30 sin 64.3. So you take your calculator, you look for the sine of 64 0.3 and you multiply by 30, you are going to get 27 times 10, that will be equal to 270.32 minus 100 times 4.9. So you are taking 100 times 4.9, that will be equal to 490. That will just be equal to 490. So if we take 270.32 minus 490, you are going to get negative. That is 270.32 minus 490. This is 219. So this is minus 219.68. This is minus h. So the height there is just equal to 219.68 meters. So the height of the building is just equal to that much, which is equal to 219.68. That is part B. So part C, calculate the landing velocity of a ball and the angle it makes to the horizontal at this instant. So to determine the angle at which this particular ball it makes to lands to the ground, then this can just be computed in this way. That we all know that at this particular point, let us take the velocity at which the ball hits the ground is v. So we could be having the horizontal component velocity as well as the vertical component velocity, which is vy. So there is an angle there. Let me take angle theta, which could just be determined there. Okay? And to determine that particular angle, we need to use the Pythagoras theorem. So we are really going to have this kind of the components, the vy and the vx there. This is to part C. So that if this is the velocity v, then we need to determine that particular angle at which this particular ball hits the ground. And to determine that, to determine the velocity v, then we use the Pythagoras theorem. That this will just be equal to vx squared plus vy squared. We take the square root of that. All know what is vx, the horizontal component velocity, and vy, the vertical component velocity. That the vx there is just equal to v naught cos theta. Remember here we are using our expression v is equal to u plus at. So the acceleration due to gravity acting to the x direction is just equal to 0. So our vx will be equal to v naught cos theta, and the vy will be equal to v naught sin theta, will be equal to v naught sin theta minus gt. So these are the values we are just going to substitute it over there. Now we can now just be able to substitute and be able to determine the square of that particular value. So for that particular case, we can be able to determine what is the vx and what is the vy. The vx is v naught cos theta. V naught is 30. We are taking with cos theta, that is cos 64.3. So we can be able to compute this to obtain what is the vx. So we are looking for the cosine of 64.3, and this is equal to 0.433, and we multiply by 30. If we multiply by 30, we are going to get 13. So the vx there is just equal to 13.0. This is in meters per second. And we can be able to determine what is the vy. Vy is v naught sin theta. So we compute for the sine of 64.3. So we compute for the sine of 64.3. And this we multiply by v naught, which is 30. So we multiply by 30. We are going to get 27. We are going to get 27. We are going to get 27.03. minus gt, that is minus 4.8 times t, the time of flight, which is 10. That will just be equal to 98. Okay, so that is 98. So if we take the difference of that, then we're going to get 27.03 minus 98. So this is equal to 70.97 minus 70.97. This is Vy. So we are substituting these values to an expression above there to get what is the V. So if we substitute to that particular expression, Vx squared, it is 13. This is equal to 169. So we add with the square of 70.97. If we square that much, we are just going to get 5,036.7. 036.74. So we add this and we find the square root. So if we add this and we find the square root, plus 169, we get 5,205.7. Taking the square root of that much, this gives us 72. So the velocity V will be equal to 72.15. This is the velocity at which that particular ball hits the ground. So we need now again to determine this angle at which this particular ball, the angle it makes to the horizontal at the instant the ball hits the ground. So to determine that particular angle, we need to determine the tangent. To determine that particular angle, we need to take the tangent. That is the tan of that particular angle theta, which will be equal to an opposite over adjacent. That is Vy over Vx. So the Vy had been obtained, which is negative 70.97 over Vx, which is 13. And if we compute this much, that is 70.97, if we divide to 13, we are going to get negative 5. We are going to get negative 5.459. So if we want to find the tan theta, then we are just going to take the tan inverse of negative 5.459, of which if we just find that particular angle, then we're just going to get the tan inverse of negative 5.459, which will be equal to negative 79.6. So the angle here is 79.6 negative, and that is angle is the negative. This angle here is negative 79.6. So that is the angle at which that particular ball hits the ground, the angle it makes to the horizontal at the moment that particular ball hits the ground. This is our first example. The second challenging area is a horizontal projection of a body at a point above the ground. This is horizontal projection from a point above the ground. Okay, this is another challenging area where we're just going to look whenever a body is being projected horizontally from a point above the ground. So we are having a case, we are having our sketch diagram like this. That the body is being projected horizontally. So the initial velocity of projection goes to the horizontal, to the x direction. Okay, and the trajectory it takes will be like that until when it lands to the ground. And we are just going to assume that this point is at a height h. That this point of projection is at a height h from the ground. And the range covered is this one here. So you might be asked to determine the time of flight from the point of projection until when it hits to the ground, or evenly the range, or evenly be able to calculate the height h. Okay, so we are using the same formula, that is S is equal to ut plus a half at squared. So that if we are looking, let's say, for the, whenever we are looking, let's say, for the time of flight, whenever we're looking for the time of flight, then we can just be able to use that particular equation, whereby y will just be equal to h, whereby will be equal to h minus v naught sin theta times t for the first expression there, and that will just be equal to minus a half times gt squared. So I'm just going to use that particular expression, and from there, as long as we are looking for the time t, then our y will just be equal to 0, and here will just be equal to h plus v naught sin theta times t minus a half times gt squared. Our interest is to determine the time t, the time of flight, so that we can take this particular expression into this way, which will just be equal to a half times gt squared minus v naught sin theta times t minus h. So the whole of this is just equal to 0. Now from this particular expression, remember that this is the horizontal projection. For horizontal projection, meaning that the angle of projection is 0. The angle of projection here, the angle of projection is 0. And the sine theta, which is equal to sine 0, is 0. So the whole of this particular expression doesn't exist. And therefore, we are just going to have a half times gt squared. The whole of this goes to 0, because the angle of projection theta there is 0. So a half gt squared, this will just be equal to h. And therefore, the t will just be equal to 2h over g. So we are having the square root of that. So this will be giving us the time of flight. So from there we can be able to determine the range r. Now the range r is determined by using the horizontal component velocity. So that whenever I'm talking about x, which is equal to the range r, we'll be taking the v naught sin theta, v naught cos theta times the time of flight. But remember, the cosine of theta is a cosine of 0. Cosine 0 is 1. So we are just going to have, if cosine of 0 is 1, then this will just be equal to v naught times t, because v naught times 1 times t is v naught times t. So this will be giving us the range r. Okay, and we can be able to know that the range r, if I'm substituting from the first expression, then the range r will just be equal to v naught times time of flight, which is equal to that much. So this is equal to 2h over g. So this will be giving us an expression for the range. So the expression for the range will be given by that particular expression. Okay, and from that we can go now and be able to see a pure example of this kind of a challenging part. And this takes us to our second example. This takes us to our second example. It says that a man is sitting on the ground, seeing an aeroplane traveling horizontally with a velocity of 100 meters per second at a height of 500 meters, dropping a luggage of medicine to the victims of COVID-19. If the luggage lands on a platform fixed on the ground, and that its horizontal distance covered is 19.2 times the height of the platform, then determine the time taken by the luggage to land on the platform and the height of the platform from the ground. So we are just going to use the same diagram, and using the same diagram, we are just going to use those expressions which had been derived. And our first part, we are looking for the time taken for the luggage to land onto that particular platform. So for that particular case, we are having a platform which will be somewhere there. We are having a platform which will be somewhere there. And this platform is at a height h. So if it is at a height h, then it means that this is at a height h. Therefore, the left height there is equal to a capital H minus small h there. So that is the actual height we are having. Now the luggage had been released and it lands to that particular ground. And the values which is given, that the V naught, the velocity of a plane is 100 meters per second. And is traveling at a height of 500. So the height h there is 500 meters above the, at that particular height, the altitude. And we are given that the distance covered, this r, is 19.2 times the height of the platform. These are the values which are given. So now we need now to determine the time taken by the luggage to land on the platform. That is part A. So to determine the time taken to land to a platform, we need now to use those particular formulas which had just been derived. To determine the time taken by the luggage to land on the platform, we are using that particular expression, that is y is equal to v naught sine theta minus a half gt squared. But to our case here, we'll now just be using y to be equal to h minus small h, this particular altitude, plus v naught sine theta, okay, v naught sine theta, it is times t, sorry, v naught sine theta times t minus a half times gt squared. And we substitute y for 0, and here we are just going to have h minus small h there, plus, now remember the sign 0 is 0, so the whole of this particular expression doesn't exist, so we are remaining with minus a half times gt squared. So h minus small h, this will be equal to a half times gt squared. Remember h, this is 500. So 500 minus h is equal to g, that is 9.8 over 2. So this will be equal to 4.9 times t squared. So we are having this particular expression. So let me take this to be as the first part. But our interest is to determine the time of flight, which is t. But we all know that this particular distance, which is x, this will just be equal to v naught cos theta times the time of flight, which is equal to t. Cosine theta is cosine 0, which is 1. So this will just be equal to v naught times t, which will just be equal to v naught times t. And this x is given, which is just equal to the range. This is just equal to 19.2 times the height of the platform. So we could just be able to first to say that the v naught times t, this is equal to 19.2 19.2 times h. 19.2 times h. And then we could just be able to, we all know what is V naught. The V naught, that is 100. So we could just take this to be equal to 100 times t to be equal to 19.2 times h. So that h, this will be equal to 100 t over 19.2. Now I substitute this particular expression h to this particular equation there. So if I substitute there, I'm just going to get 500. I'm just going to get 500 minus h, which is 100t. 100t over 19.2. 19.2 is equal to 4.9 t squared. So if I write in a very good way, then I'm just going to get 4.9 t squared. This is the quadratic equation. So I take this to that particular side, which is equal to 100 over 19.2. 100 over 19.2. And if you take that is, so this will be equal to 5.208 t, and therefore this will be equal to minus 500 equal to 0. Now if you look, this is a quadratic equation. If you solve this quadratic equation, you will get two values of the time t. One will be negative and the other will be positive. So we pick up the one which is positive. One of the time is 9.58 second, and the second time this will be negative, which is negative 10.664 seconds. So we are neglecting the one with negative value. We are going to pick the one which is positive, and that is the time taken by the luggage to land on the platform. If we go to part B, we are looking the height of the platform from the ground. The height of the platform from the ground. The height of the platform from the ground, this is part B, can easily solved using this expression. This expression, because the time t had already been calculated. So the height h is equal to 100 times t. This is equal to 100 times 9.58. We divide by 19.2. So we can just be able to get the value for h so straight. That is 100 times 9.58. This will be equal to 958 over 19.2. So we divide that particular value so straight. 49.89, almost about 50 meters. About 50 meters. So the height of the platform H, this is almost about 50 meters from the ground. That is part B. This is the second part of our challenging, which is very challenging to most of the students. So those are the basic challenges of which most of the students really faces. But as long as you remember those basic four formulas, then you can just be able to play with them to whatever any question will just be able to, you are just going to meet, you can just be able to use to solve that particular problem. So that is, that we can be able to say that we can be able to look some more challenging problems in our next period. Thank you very much for listening, but now I could just be able to allow some questions just to ask me for, you can just be able to ask me by sending me a message, a question using the number which is passing down there. Just ask me and probably I can just be able to share with you whatever, any problem you are having with regard to a projectile motion. Okay students, there is one of you have just asked me a question. This is John from Babati. You have just asked by sending to me a question here, and I can just be able to read it to you. A boy standing on the top of the tall platform, which is 50 meters high, kicks a ball at an angle of 30 to the horizontal with a velocity of 16 meters per second. A second boy standing at a distance of 70 meters from the foot of the platform starts running to meet the ball. At the instant it is kicked. How fast must a boy run in order to catch the ball before it hits the ground? Okay, so you have heard this particular question. There is a boy standing at the top of the tall building, kicks a ball at an angle of 30 to the horizontal with a velocity of 16 meters per second. And the height of the building is given there, that is 50 meters. Now there is another ball from the foot of the building, 70 meters, standing there. He is now just have to, as at the moment the boy kicks the ball, that particular boy, another boy, runs towards the building to catch the ball. Now the question is how fast that particular ball should have to run so as to catch the ball at the moment it just hits the ground. So this is a question which is really very clear. Now with this particular question, we are having something like this. We are having a ball which is there, is kicked with a certain velocity v0 at a certain angle theta. So that particular ball goes like that. That particular ball goes like that. It lands to that particular ground. Now there is another boy there. At a distance of 70 meters. Okay. At the moment the ball is kicked, he begins to run towards this direction. Now with what velocity, with what speed, this man should have to run to this direction, so as at the moment he reaches here, the ball also reaches there. So what is really very important with this question, though I'm not going to compute it, to solve it mathematically, what you're supposed to know is to determine the time of flight, of which you have already looked to our first case, that you can be able to determine the time of flight from at the moment this ball, it's kicked here until when it lands to the ground. That particular time of flight will just be the same as the time this particular boy should have to use to reach to the same point where that particular ball strikes the ground. So the coincidence of that particular time, which are the same, could just be calculated. Having known that particular time, which is, let me call it to be equal to t or t1, then the second thing you need to determine the range, this range here. Having known the velocity here is given to be equal to 16 meters per second, and the angle of projection there is 30 degrees to the horizontal. You can be able to determine the range, of which in our first case we have done this whenever we talk about the projection at a point above the ground. So you could be able to determine the range r. Having obtained the range r, you could be able to deduct from the total distance, which is 70 meters, and you will remain with a certain distance here. Let me call it a certain distance. Let me call it R1. So having obtained R1, and you know the time for this boy to cover this distance R1 is equal to that particular time t, then you can just be able to determine the speed at which this boy should have to run to that particular point so as to catch the ball just before that particular ball hits the ground. So that particular speed, which is v, will just be equal to the distance s over the time t. The distance, this much, could just be calculated there, and the time t you could have already solved in the first part, and eventually you will just be able to determine the velocity or the speed of that particular ball which he has just to run so as to catch the ball just at the moment that particular ball hits the ground. I hope you have already understood, my dear student, and all the students who are just hearing. Okay, with this, there are so many questions, but it's not possible to go through all of the questions. But I believe next time, whenever we meet again, we will be in a position probably to discuss some more challenging questions from you, and as well as I could be able to cite out some other areas which are really more challenging in a projectile emotion, so that I could be able to share with you and be able to see some more solutions. But all in all of those questions of projectile emotions are not difficult, as long as you remember those 4 basic formulas, and evenly how you can just be able to use them in solving all other questions. Thank you very much, and see you next time.